So now we want to prove this pivot theorem. If you have some constant times n times log n many edges, then we can find the k-regular subgraph. So our idea is roughly as follows. So we know that if we have a regular bipartite graph, say R regular, it has basically any k regular, it contains any k regular subgraph for all k smaller than or equal to R. Because it has a perfect matching, so you take out one perfect matching, and you can take out another perfect matching. And once you take out, the remaining thing is again regular, so you can keep taking out so that you can get all k regular subgraph. So instead of finding k regular subgraph, we want to say if say p is bigger than k, then it's enough to find the bipartite p regular subgraph. And then for that, how we want to do it is roughly as follows. So we want to find some matching covering some vertex set, say, I don't know, P1, some vertex in P1. And then you find the second matching. So these edges are already used up, so we don't consider this anymore, so those are deleted. And in the remaining graph, inside of this P1, we find the second matching. And then we say that the P2 is the one in there. And then we find the third perfect matching. Third matching. And then let's say this is V3, and so on. We keep do that. We have V1, V2, V3 here. And while you're doing that, what happens if P1 and P2 and P3 have to be the same? Then this immediately gives there are three matchings covering the same set. So this immediately gives us three regular subgraph, three regular graph. But moreover, if we know that even if they are not same, if V3 is not so smaller than V1, that means we have a graph on V1 which contains many vertices, and then second matching is almost as big as this, and then third matching is also almost as big as the perfect matching. So here, now its average degree is almost 3. Let's say instead of 3, you have this, say, BK. Then, and all of them has almost same size. It's not so small than P1. Then average degree is almost K. Very close to K. And maximum degree is K. So we consider this subgraph, which only consists of these edges from the matching. Then what we get is a graph whose average degree and maximum degree are not too far. So we can apply this theorem. So this theorem says that if maximum degree and average degree are close, which is the difference is at most 1, then we get the regular subgraph. So if this happens, then we get what we want. So in other words, in this sequence, the set size must decrease too fast. But we will use this, fact that we have this many edges. We want to, show that it cannot decrease too fast. So that's basically how we will proceed. So let's prove. So let D be the average degree of G. And let's define this terminology. We say that a bipartite graph with parts x and y is R half regular if x is as big as y and every vertex in the bigger part has degree R. Then this is R half bipartite. And let's prove this claim. So this R half bipartite graph we have, will be the each of these, vertexes. So our plan is when we have an R half bipartite graph, we find some matching covering Y. And then, no, not that. So we find some smaller half regular graph with a perfect matching. And then we delete the perfect matching and we shrink. So this bigger set is B1, and then now here is B2. And you delete this perfect matching, and then now you have another R-1 half bipartite graph, and you shrink to a smaller one which has a perfect matching and half bipartite, half regular, and you delete the perfect matching and you repeat. This is how you get matchings which are shrinking each time. So for that purpose, we prove this lemma. If you have a R half regular bipartite graph with bipartition X union Y, then it contains a smaller R half regular subgraph with a perfect matching. The proof is simple. So you have X and Y, and you know that X is as big as Y. Then we want to use Hall theorems to find the perfect matching in the smaller subgraph. So we artificially take a vertex set here which automatically satisfies the Hall's condition. So let us be a non-empty set which is minimal with respect to the following. Minimal subset of X with its neighborhood has smaller size than S. So by taking this as a minimal subset satisfying this, if you take all smaller one, its neighborhood must be bigger. So this smaller one is S prime, then neighborhood of S prime must be bigger than S. Because otherwise this is a smaller set than S which satisfy this. So such S actually exists because X is bigger than or equal to the size of S. Such a set must exist. And we have the size of S and size of neighborhood is same by the minimality. Because if its neighborhood is strictly smaller than S, then we can actually, find one, vertex and we kick out, and the rest of them has a, let's say this is X, then the neighborhood of S minus X has size smaller than or equal to neighborhood of S, size of S, and then you know that this is S minus 1, which is S minus X. So this is contradiction to the minimality of S. So we know that this equality must hold. So yeah, this part is, if we assume this, then we get a contradiction of minimality. So we get this. And again, by the minimality, holds condition holds. For the subgraph induced by S and its neighborhood, and it has a perfect matching. And this proves the claim. So now we start the proof of the theorem. So we take a maximum bipartite graph. Bipartite graph with a maximum number of edges. So we partition the vertex into A and B with maximum number of cross edges between A and B. Then we obtain a bipartite graph. G prime of G, bipartite subgraph, with average degree at least T over 2. So we know that every graph has a bipartite subgraph with the number of edges at least half. And note that if we delete any vertex with degree smaller than T over 4, does not decrease average degree. So we delete all such vertices, then we obtain G double prime, which is subgraph of G, is a bipartite, and minimum degree of G double prime is at least T over 4. And let x0 and y0 be the bipartition of G double prime with x0 as large as y0. So and you have bipartite graph, and then here we have edges. And if some vertex has high degree, then we can delete this. We can keep delete some edges so that all the vertices here has the same degree. So let R sub I be T over 4 minus I for each R from 1 to, say, natural number and 0. So we delete some edges to obtain a subgraph H0 of G with, every vertex in X0 has degree exactly R0 in H0. So this is R0 half regular. So we have this x0, y0. This is R0 half regular. Let's draw this a bit big. By applying claim, the above claim, find the R0 half regular graph. Subgraph, say G0 inside of H0 with bipartition X1 and Y1 with X1 is in X0 and Y1 is in Y0, having a perfect matching, say F1. So you find some X1 and Y1, some perfect matching here. So and let H1 be the G0 and minus F1. And we repeat. So this is R1 half regular graph. So this is R1 half regular. R1 is 1 less than R0. And here again you apply the claim. Then you find the X2 and Y2. And then inside there it is R0, R1 half regular. And it contains a perfect matching. Then you take out the perfect matching, and then remaining graph is H2, which is R2 half regular. And we keep repeat. Repeat this procedure to obtain Ri half regular. Graphs H1, H2, and matchings F1, F2, and so on. And for each I, which is between 0 and R0 minus 1, we let Ni be the size of xi. Then fi contains exactly Ni edges. So now we have our sequence of matchings. So now we want to argue as before. If they shrink too fast, then we will get a contradiction on the assumption that there are many edges. And if they don't shrink too fast, then we will find the regular subgraph there. So for that, the previous theorem, no, not the theorem, previous theorem by Alon, Friedland, Carlyle, we need to assume that P is prime. So let P be a prime which is between P, K, and 2K. So by Bertrand's postulate, we know that for every K, there exists a prime between K and 2K. So we can find such P. And for each J, which is between 1 and R0 minus 1, we let Rj be the graph, which is union of where I is from j to j plus 2p minus 2 fi. So this is union of 2p minus 1 consecutive matchings. So which is exactly the sequence of this perfect matching. We write it and then we take the consecutive one together. What do we know? If the smallest one has this many edges and largest one has n sub j this many edges, if this is bigger than, not smaller than this number, 2p minus 2 over 2p minus 1 for some j, then Rj contains, say, 2 nj vertices, because each of these perfect matchings are shrinking, so the xj and yj and then xj plus 1, yj plus 1, they are keep shrinking. So if you take the union, the vertex set is this. And each of the matching has size at least this number, n sub j plus 2p minus 2. And it has at least 2p minus 1 matchings, and each of the matching has at least n sub j plus 2p minus 2 edges. So this many edges. Hence, it has average degree at least how many? 2nj under 2p minus 1 times nj plus 2p minus 2 times 2. This is number of edges. Twice the number of edges over the number of vertices is the average degree. So this is n 2p minus 1 times n sub j plus 2p minus 2 over n sub j. And by our assumption, we said that this is at least as large as 2p minus 2 over 2p minus 1. So this is bigger than 2p minus 2. Moreover, as it is a union of 2p minus 1 matchings, so it has max degree and most 2p minus 1. So by the previous theorem, theorem 4.47 implies that Rj contains a p-regular subgraph. So G contains a p-regular bipartite subgraph. As every regular bipartite subgraph contains a perfect matching, you delete the perfect matching p minus k time. So it contains a k-regular subgraph. So in this case, we are done. So hence, we may assume that this is not the case, meaning that for all j between 1 and r0 minus 1, we have that n sub j plus 2p minus 1, no 2, over nj is at most 2p minus 2 over 2p minus 1. So we assume that it actually shrinks quite fast. However, then what do we get? You can keep do that until you have, give me a moment. So you keep do that until you have a r sub 0 minus 1. So we know that the nth of R0 minus 2 must be, we know that R0 minus, give me a moment. What was Ni? So we know that the R0 and then R sub, R0 minus 2, this is exactly 2. So in order to get the two regular graph, we know that each part must have two vertices. If there is only one vertex and one vertex here, and between them it's one half regular, it cannot be two half regular. So we know that R sub n sub R0 minus 2 is at least 2. And also, because of this condition, this is n0 times, you shrink this many times, this. So starting from R0, you go to R0 half regular to 2 half regular, and every 2p minus 1 time, you shrink by more than 2p minus 2 over 2p minus 1. So how many times do you shrink by this much? Is R0 minus 2 over 2p minus 2. So this many times you shrink by this many factor. Then you get this 2. So you get this inequality. And what's n0? n0 is at most n. And what's this number? This number is 1 minus 1 over 2p minus 1 to the R0 minus 2 2p minus 2. This is roughly e to the negative 2p minus 1, 2p minus 2, and R0 minus 2. So you can actually bound this by R0 minus 2 over, say, 4p square. So we have this. What do we know? We know that this R0, what was the R0? R0 is d over 4. Many is 4, so this is at least 20k square log n, ln, natural log n. And p is at most 2k. Then what does it mean? Then n times e to the minus roughly 20k square log n over, say, 4k square, 16k square, okay. But this is smaller than 2, because e to the negative ln n is already 1 over n, but this is bigger than that. So we know that this is smaller than 2, which is a contradiction. So that means this sequence cannot shrink too fast. So there must be some 2p minus 2 consecutive ones that doesn't shrink too much. Then for that, you take the union. Then it's a bipartite graph whose maximum degree and average degree are not too far. And we can apply the previous Allon, Friedland, Carlisle theorem to get the regular graph. So this proved the theorem. As I mentioned before, we know that we know this theorem, but as a lower bound, we know that there exists a graph with n log n edges, which contains no k regular subgraph for any k. So there are still gap between that. So what would be the, maximum number of edges in a graph without a k regular subgraph? Then it's between n log n and n log n. So determining that would be also interesting open problem.